The team is back with another episode of Topical Explainers for the last chapter of CAIE AS Level 1 Mathematics. In this video, we will be discussing all about integration, and to simplify the topic and provide us with all the information we need, we have Pratyush.
Hello guys. Um, we will be doing integration today, which is the 8th and final chapter of AS level maths. We'll be covering basic integration, integration of a linear factor, definite and indefinite integrals, areas under curves, improper integrals, and volumes of rotation. So let's get into it. For this chapter, the main thing is you must have completed differentiation. Without knowing how to differentiate, integration will not make much sense. You also need to be confident with your algebra, functions as well. That's an important part. Coordinate geometry, because it relates to the Cartesian plane a lot. X and Y coordinate. Quadratics helps a bit. And you need to know your indices and exponents. What to the power what makes what. So the rules of that. Okay, let's get started. So first we need to understand the concept of integration. Imagine you have a derivative and you want to find the original equation again. So dy dx equals 6x. What does y equal? Well, we know that to differentiate something, like in the form of, it's like an algebraic thing here, 6x, we know that we multiply by the power, then decrease the power by 1. So it's, let's say we have x to the power n. We differentiate it, we get n times x, and we decrease n by 1. So imagine going backwards. What do you do? Well, I would first increase n by 1 and then divide by n. Divide by that new n. So we'll look at this in more detail later. But for now, let's just look at this example here. So 6x to the power 1, I'm going to increase the power of x by 1. So x squared. And I'm going to divide by 2. This gives me 3x squared. But we'll find out later you have to add plus c as well. Well, I'll show you why in just a minute. Here we're just looking at the basic concept. The reverse of integration is called, reverse of differentiation is called integration. You'll hear a lot of different names like antiderivative, stuff like that. Why do we want to do this? Well, it's useful for finding the area of a curve, the area under a curve, and the exact area, not just an approximation by counting boxes. And it's used all over the place in maths and science and even statistics, economics as well. Like imagine an MRI thing, you're finding areas and volumes, or a lot of different stuff. Normal distribution, that stat stuff. Okay, so we know that integration is useful. Now, how do we do it? Well, here's the rule written out for you. If we have a derivative and we want to find the original function, we integrate. So this is basically saying if you want to go from the derivative to the normal function, you're integrating, right? So if I want to integrate a n to the power x, what do? Well, I increase the power of n by 1, then divide by that new power, n plus 1, and the plus c there. So put write the rule for yourself in words. Increase power by 1 and divide by the new power. Now let's find out where the plus c comes from. Imagine differentiating something like 6x plus 2. You would just get 6, right? Let's say that's dy dx. And we lose the constant term. That's why when we go back to from the derivative to the normal function, or from the function we integrate an expression, we have to add a plus c on the end, that signifies we don't know what that constant term was. The c stands for constant, because we lose that constant. And going back, we need to just put a little plus c in place of that constant. Okay. And little thing to note here, this works for any power of n rational other than -1. There's a special rule for -1 that we don't learn at AS level. Oh, good practice to know how to read integrals out loud. I would read this as integrate a times x to the power n with respect to x. With respect to, just a handy little thing to know if you want to read stuff out in the classroom. Okay, let's practice some of the following. If you have two terms like this, same as differentiating, you can integrate 6, that's a horrible integral sign, 6x, and then you can integrate minus 8x, 8. You can put the minus sign outside or you can put it inside. It doesn't really matter since it's a constant. It's like a -1 constant. So we can do each separately. We can first increase the power, do 6x to the power 2. That goes to 3. Divide by 3. And then for 8, I just go 8 times constant term. Constant term is x to the power 0. X to the power 0. You can think of it like that. So I'm going to increase to x to the power 1, which just becomes x, divide by 1. So that's a constant, and then please see. So constant becomes just times the x. This one we can simplify to 2x cubed minus 8x plus c. So that's for the first one. Let's do the second one really quickly, now that we know how to do it. The root sign applies to both 9 and the x, we know that. So it's going to be 3 over root x, which I'm going to write as x to the power half. And in fact, since it's divided by x to the power half, I can also write that as x to the power minus a half. And then I'm going to write the next one, 4 to the power x minus 3. So I'm going to integrate this. Increase this by 1. So it's 3 x to the power minus half plus 1 is plus half. I'll write the plus just for clarity, and divide it by half. And minus 4x increased power. 3 minus 3 plus 1 is minus 2. Divide by minus 2. And this simplifies down to 6x to the power half, or you can write root x, minus, for important thing, plus c. Always remember the plus c. This is indefinite, since it's an integral, always write plus c. There's a mark for plus c, guys. It's not just a little fun thing we put on. And it represents something important. Okay, minus 4 divided by 2. This is plus 2 x to the power minus 2. So it's, plus c again. So this is our integral for this. Okay, that's the basics. Increase power by 1, divide by that new power. What about if we have a linear factor to power? Remember in the chain rule, we differentiated stuff like this. And in the chain rule, you could do anything. You could do not just a linear factor, you could do 3x squared plus 5 to the power 10. But in integration, we can't. There's stuff that applies, and we can only, this rule only works for linear factors, the x to the power 1s only. So what's the thing going on here? Well, here's the rule written. Looks a bit scary, but do not be scared. Same thing. We use this power. We increase that power by 1, divide by the new power, and we divide by the coefficient of x as well. I like to think of this as a reverse chain rule, sort of. Because in the chain rule, if you differentiated this, you would differentiate this function, you'd put to the power 9, right? if if you differentiate, then you'd put the 3 outside because you take derivative of this, multiply by the 3. You'd multiply by the derivative of the stuff inside the brackets for differentiation, but in integration, we divide by it, not multiply. Okay. So let's solve the equations. For this one, I'm going to do 3x plus 5. I'm going to increase the power by 1, 11. And then I'm going to divide by that power, 11. I'm going to multiply by the derivative, by the coefficient of x. So I'm going to multiply by 3. Yeah, wait, no. I've just done it. So once I've done the operation, the signs disappear. Remember my plus c. So this is 3x plus 5 to the power 11 over 33 plus c. That's my derivative. That's my what do you call the product of integration? Is there a name for it, Vyomesh? Do you know?
Product of integration?
Like the thing you get out of integration. Like you differentiate and you get a
Oh,
derivative. You integrate and you get a.
actually, yeah, that's a good question. Even I don't know. Let me check.
I'd look it up, but just the thing you get from integration for now. You guys can do a bit of research if you want, viewers. This one it's on the bottom of the fraction, so I'm going to write it as. Remember, the root is like a power a half, and it's on the bottom, so I can write this as 2x plus 1 root half, and it's on the bottom, so minus 1 half. Now I can apply the same thing, increase power by 1. Oh, this is the function I want to differentiate. And now I want to integrate. I keep saying differentiate. Increase power by 1, 2x plus 1 around the brackets, plus 1 half. And then I'm going to divide by 1 half, and then the thing inside the brackets. So 2. These two cancel. So my answer, plus c, my answer just becomes 2x plus 1 square root plus c. Okay, that's my answer for this integral. Hope that makes sense. Remember, this only works for linear factors. There should be no squared or cubed or whatever for that x. It's just ax plus b to the power n. Same rule, divide by a as well. And again, not my n is not minus 1. Okay. We've done some integration basics. And why do we use this? Well, let's say we were finding the value of y when we were given dy dx, right? We're finding the original curve from its gradient function. And one problem that comes up is we were left with that plus c. You can't have a equation for a curve with just a plus c sitting around. You need a solid number for that, don't you? Like plus 8. So how do we find that? Well, the idea is simple. Oh, what is this? Okay. You are always, or usually, in any case, you have the information you require to find a point on the curve, and you can substitute in the x and y values into your equation of the curve and find c. Instead of me talking about it, you can just do it here. The gradient of the curve is half x, and the point 3, 7 lies on that curve. Find the equation of the curve. Okay, I'm going to write the gradient, which means dy dx, is half x, and the point 3, 7 lies on the curve. First, I'm going to integrate this to get y. So I can write this as integrate half x with respect to x. How do I do that? Same rule from before. Increase power by 1, half x to the power 2, divide by 2. That just becomes 1/4 x squared. So y is quarter x squared, and this point lies on that curve. So what do? I substitute in x, y here. So 7. Oh, wait. Plus c, guys, remember. Because it's an integral. Plus c. And so I now put in my values of x and y. 7 equals 1/4. X is 3. 3 squared plus c. Now I can just get c by itself by bring everything to one side. 7 minus, all right, 3 squared over 4. So c is equal to 7 minus 9 over 4. 19 over 4. So the equation of my curve is thus 1/4 x squared. And now I can replace the plus c with the value of c I found. So
By
this
the way,
is,
yeah. I just wanted to add something. To some people, this may be confusing, what I'm about to say. But essentially, looking at the first step, right? It says dy upon dx equals to 1 upon 2x. Essentially, how we got the integral signs is that imagine that the dx goes to the right, it gets multiplied, and
Mhm.
on the left, it's going to be 1 times dy. So essentially, it's like an integration of 1 with respect to y on the left hand side. And on the right hand side, it's going to be integration of 1 upon 2x with respect to dx. Yeah, like that. And so, like this, we essentially add these integral signs. And on the left hand side, 1 integrated with respect to y would just be y. Because we imagine it as like y to the power 0. So we increase the 0 to the 1 and then divide it by 1. Because that's just going to turn into y. And then that's how we kind of like get the whole integral thing out of dy upon dx. It's just like a simple explanation of how we do things. But yeah, that's it.
yeah. This stuff comes in really useful later on. Once you're doing full blown integration, you have to do differential equations and stuff. This is a good technique. You can separate the things, and it's good to understand the concept as well. Thanks, Vimish. So,
It might be
right,
confusing though, but like
yeah, yeah.
if
If
you
you're confused
understand,
by this, don't worry
yeah,
about it.
it's not something that is very necessary to understand. It just improves your understanding of the concept itself.
Mhm. Okay, so you can remember whenever you're trying to find c, plug in x and y values and find c. That's all there is to finding c. Okay, and now we move on to the bounds, the realms where c does not need to appear. Okay, why is my function not here? There you go. A function that we get from integration is called indefinite integral. So far we've been doing stuff like integrate x dx, and we get um, x squared by 2 plus c. And this is like a function. It's just an expression. That says just an expression, right? You put it on the Cartesian plane, just make some sort of curve or line, and it has no bounds. Like it'll just keep going. By contrast, a definite integral represents a number value. Like while this is an expression, right? It'll make a graph or whatever, but it's not a number because there's a variable in there. A definite integral does not, once you finish it, once you get the final value, there's no variables, it's just a number. Let's see how to get that. Here we can see there's a lower bound and an upper bound, a and b respectively. And the way we do it is, if we have a definite integral, we first integrate it, and we get the integrate. You can keep the bounds here to remind yourself, a and b. And then the function we get, the expression, we plug in our values of lower bound and upper bound. We subtract the function, substituting in x as upper bound, and substitute from, wait, what is that, right? No,
Oh
I
yeah,
think I
that
wrote
is
this the
correct. Yeah.
wrong way around. Did I?
It should be from the oh from oh yeah, it should be f up minus f low.
Wait.
So like
Oh yeah,
yeah,
this
the
is
wording
fine.
makes
Just
seem
the
as
letters
if
are
that's it.
confusing me. All right. From this upper bound, we subtract the lower bound. So you just plug in the bounds to the function, like whatever the value of x is, you put it as that. This is why you need to know about functions. And here's a good point. What happened to our plus c? Why do we end up with a number without a c? Well, imagine this function have as f of x is, let's say it's r x squared by 2 plus c, right? And if we do, let's say no, fb, fb minus fa, then that's b squared by 2 plus c. Make sure, since it's the whole thing, you subtract it. It's going to be a squared by 2 plus c. When we open the brackets, this becomes minus c minus a squared by 2. This is plus c, b squared by 2. And the plus c and the minus c, they cancel each other. So we're just left by b squared plus a minus a squared by 2. So the plus c effectively gets cancelled in a definite integral. So we're just left with a number value. Using that knowledge, let's solve this one here, this definite integral. First, we have to get rid of the integral. So we must integrate. We're going to integrate 2x plus minus 1 plus 4. It's a linear factor to a power of 4. So let's solve this. I'm going to do 2x minus 1. I'm going to increase the power by 1 to 5. I'm going to divide by 5. I'm also going to divide by the factor of the x times 2. Gives me, and where I would put plus c and be done with it normally, this is a definite integral with bounds. So what I like to do is put nice square brackets around it, write 1 and 2, and now I can get the values.
Wait, just
So
one question by the way.
uh,
Like in P1, they don't have it when the bounds are like flipped. Like the upper bound is less in value than the lower bound.
oh, that's a good point, and I think it's actually a good important thing to know as well. Thanks for bringing it up. If the bounds are flipped, and instead we subtract fa from fb, because our bounds were ba instead of ab, then what happens is the value comes out negative, because you can see we've just basically multiplied by some minus 1 to flip this. And that's why if your bounds are flipped, you're going to get a negative value. Later on when we're
Essentially,
coming to...
like yeah. Essentially, what
Sorry?
he means by flipped is that when the up like a value is less than the b value.
Yeah.
So like in normal case scenarios, the value on the top is going to be more than the value on the bottom. But yeah, I'm not sure if it comes in P1 yet, but if it does, at least that's a point that we could remember.
Mm. And this might come in helpful later as well, because once we start doing areas, sometimes your area will come out negative. And you can flip bounds to fix that. And later in P3 or in P2, definitely you do need to sometimes be aware of flipping bounds to solve and get them in the right form. But for now, let's just carry on. It's just a good piece of info to know. Thanks, Vim. Right, so we were solving this in depth. We integrated our function, and we have our bounds here. To get rid of the bounds, we're gonna do fb minus fa. So f of 2 minus f of 1. So I'm just gonna plug in the values. 2 times 2 minus 1 power 5 by 10 minus 1 times 2 minus 1 power 5 by 10. And evaluating this will give 2 times 2, that's 4. Minus 1, 3. 3 to the power. Okay, big number here. 10. 3 to the power 5 over 10 by 1 to the power 5 by 10. Oh, not that big of a number. Okay. That's odd. Wait, I was expecting a bigger number. Can you just cross-check this for me?
Yeah, sure. I'm gonna show an unethical hack after this.
Okay. So that gave me 24.2 for some reason.
I got 24.22. Yeah.
Okay.
I mean, yeah, like
Yeah, yeah,
24.2.
yeah.
T
As
O
well.
O O.
Okay.
Essentially, the hack is this that for definite integrals,
Mhm.
only do this for cross-checking, by the way. There is an
Oh,
option to do definite integrals in most calculators. I'm
definitely.
not sure if you can see this, but if on the top right side, there should be a character for definite integrals, and it's gonna look like something like this. Essentially, what it's gonna do is that it's gonna get you could put in the values, the limits, and then it would give you the definite integral value. This I've checked with CAIE's handbook too regarding this. It's technically allowed. They do allow definite integrals to be solved like this, and also definite derivatives, where you know the value of x. Let's say if you want to find the gradient at a certain point. That same thing, if you just press shift and the integral sign on the Casio FX991EX, it gives you that too. Two things are allowed, but to get all of the points, it is essential for you to also write the working out.
Definitely. I've used this multiple times to check, and for the AS level, it's it's pretty helpful because most of your answers will be whole numbers or fractions, and the calculator can display them just fine. Once you
Bro,
start getting
like
to like
seriously, the
P2,
amount of
P3,
questions that I like, such big questions where I'm too
mhm,
lazy to go through every single step of the working out. I just use this for to cross check at the end.
definitely
It's
saves
so
so much
helpful.
time. Later on, you might start getting numbers like pi or e or something, and then your calculator can't display stuff properly, like root 2 times pi. It won't display that.
Oh yeah,
So
that is happen.
just beware though. If it wants an exact answer, sometimes you can't just do that. But you can always check, right?
Yeah, that's actually something that I've occurred through a lot of times. In cases that you get like very long decimal points, right? What
Hmm.
I do is that the answer that I got, I also calculate that and I turn that into decimals to see if it
And
is
check if
like
they're
similar
equal.
value.
Yeah.
Yeah.
So that's a good thing. So this is just like that quadratic thing solver thing. Like help you save time. It'll help you check your answers, but don't just ignore integration because oh I have my calculator. Just use it as a checking tool, guys. Okay. Now we come on to the meaty part of this chapter, areas. We can use definite integrals to find the area under a curve between lower bound A, upper bound B. How? It's actually a pretty fun thing to show you guys here. Imagine our curve, right? That's the curve. And I want to find this shaded area A. We're going to cut it up into a bunch of strips. This is just like with differentiation where we cut it into really small lines. But with these strips, we're trying to find the area, right? And what's the area of the strip? Well, it's imagine D as in a very small increment, right? So between, oh my gosh, between, oh, what is happening? Here to here is dx, and a height is y. Of no, well, the height is obviously y because it said y, right? And we're cutting it into lots of strips. Each strip is dx wide and y tall. So the area of that box is y times dx. And now, if we add all of those strips together, we get the whole area. And you can think of the integral sign as add them all together. Like you know this sigma sign, right? Hopefully from stats. That means add everything together. Might do y dx. But when we're dealing with d, like the really tiny bits, what we write is the integral sign. It even looks like a little s. You can take them sum of all of y times little bit of x. Yes. So we're just adding up all the y times little bit of x's. That's where that integral comes from. I don't think that's fully accurate, but it helps give a picture. Um, but we're not just adding everything under the curve, and we can't add everything under the curve unless we want to go from infinity to that's infinity to infinity. No, what we're doing is we're only getting the bits between a and b. So we do this by adding our bounds. Looks like that, from a to b. I like to think of this as um, area everything under b, a versus everything to one side of a, everything one side of b, and their difference, because remember, in their difference comes out to this much. um whatever you want to do, because when you're subtracting these, remember, you subtract the bounds that you plug in, and the difference gives us just this bit. That's why you use definite integrals. Okay, that's the concept, that's the theory, that's where it comes from, using the idea of limits. Remember, dx approaches 0 and all that. Dx gets very tiny, so each strip does look like a rectangle, even though it's not actually a rectangle because it's curved. But at that scale, you know. Thus, that's where the idea comes from. Now, you don't need to prove all this in a test. What you do need to do is find areas. Drawing a sketch is usually helpful, but you'll find that a lot of questions with integration and differentiation, you will be given a diagram with scales and everything. Um, Identify your upper and lower bounds. This is an important thing. If you want to find an area like that, right, curve xy, where do you want to start and where do you want to end? You need to know that. And here's a good question, right? A lot of questions you'll see area bounded by. And what this means is if I have a curve like that, area bounded by this curve and the x-axis is here. Bounded by, it means makes a closed shape. So if I imagine, change color here. If I imagine this curve and the x-axis, see, it makes a closed shape. That means it's bounded. By contrast, stuff below it, these curves, this is, let's say this is minus x squared plus 5. These don't bound anything. They just keep going here, keep going larger. They don't bound anything. They're just lines. Which is why when it says bounded by, we only want this area here. Where'd my pen go? Here. So let's try this question now. Oh, why does y equal 0? That's where it crosses the x-axis. Usually it'll ask you bounded by the axis. We'll get to more specific cases later. Let's try this now. Area bounded by this curve and the x-axis. Helpful to draw a sketch first, so I will here. So it's given in factor form, so I can just see where it crosses the axis. 1, it crosses at x equals 0, y equals x equals 0. 1 crosses x equals 2, minus 2. Question is it a smile up down or is it a down up? Does it really matter? Probably does. Here,
It's kind
I'm
of
gonna
weird to be honest because like it's a cubic equation. I
yeah.
guess we have to do something like that, yeah. But at the same time,
That's
what I would personally do is that also maybe graph it a bit, like maybe calculate some values, like let's say the
mhm.
value -1.
Yeah,
If
that's a
it
good
is like
way to do it.
positive, it should be like that, you know?
Yeah. -1 times 1 times -3 plus 2. Yeah, okay. So at
So yeah,
-1
that's
we
correct
get
shape.
value 3. So it looks like that somewhat. Should be more symmetrical, but whatever. There you go. And it wants the area bounded by this curve. So I'm only looking for the areas which make a closed shape with the x-axis. So this makes a closed shape. This makes a closed shape. These go up into infinity, however high they want. Do not make a closed shape. So I want the sum of these two areas. Now, one thing you will find out as quite soon when you start doing integrals like these is that areas above the x-axis are positive, while areas below the x-axis are negative. If we were to take an area clean from this bound to this bound, -2 to 2, the two areas would cancel each other out, the positive and negative, and we won't get anything at all because they're the same size in this case. Which is why we have to actually take an integral here and an integral here. The bounds should be with one with bound this and one with bound that. Let's yeah, take care of the regions will have negative area, which is what I'm trying to say. So let's solve this. First thing, I'm going to multiply everything out so I can do the integral. X, I'm going to do the quadratic first. X squared. Oh, it's a difference of two squares, isn't it? -4. So x cubed minus 4x. That's my y. Now I'm going to not dy dx, integrate y. I'm going to integrate y with respect to x. Oh, one thing, the areas are positive because here the y values are positive, and here the y values are negative. That when you multiply it, it gets positive, negative. Fun fact. Okay, back here. X cubed plus 4 minus 4x. This is the same as is saying integrate x cubed minus 4x dx. And we're going to put in our bounds in a bit. Just hold on. Let's integrate this first. X cubed minus 4x. X power 4 over 4 minus 4x squared minus 2 by 2 plus c we can keep in brackets here. And now what I want to do is I want to try this from -2 to 0, and I'm going to do it again from 0 to 2. Or I could just, in this case, I could do 1 and double it, but I will do it fully. So let's do it from 0 to -2 to 0 first. Goes. Whoa. My presentation disappeared. X is x. Did it again. X cubed by. Okay, so I'm going to speed run this. 2x squared. And I'm going to do this from.
By the
Okay.
way, why didn't you put like a plus C outside of the box there?
Oh, that's just we do a plus c when it's an indefinite, but since I put the bounds in 0 and -2, the plus c kind of goes away because we're subtracting two things.
Oh, okay.
It wasn't clear, my bad. 0 to 2. At 0, it's from the upper bound is 0 upper bound because x is 0, and at the lower bound we can plug in the values to get 2 power 4 minus 2 times 2 square minus 8. So our area here is minus 8. This area is minus 8 here. Units squared.
Weird though. Like, it's usually negative when it's like under the x-axis.
Wait, that's right. Did I do something? Wait. Minus 1 times 1. Upper bound minus lower bound.
I got -4. I mean, +4 for the
Oh,
area. Essentially, when I put -2 there, right? There's actually another strat that I use a lot because
go ahead.
sometimes putting a lot of these values is actually quite confusing. What I just do is that I make the value of x equal to like whatever, let's say -2, right? I do like -2 STO on my calculator and then x, and I just rewrite the whole equation. So like x square, oh wait, x to the power 4 upon 4 minus 2x square, and I get -4. So it's like 0 minus -4. And so for that, I got 4.
Oh, right.
Let me
Minus
also
minus
go
4.
and do the integration, the definite integration on my calculator to see if that value is correct.
So here we get +4. And if you go from 0 to 2, you should get -4. Probably.
Yeah, it's 4, the value. So that's good.
So what Vyom was saying was that comes out to 0. That comes out to -4, which is why we get +4 for 0 to 2 -2 bound. And for f of f upper bound is 2 minus f of 0, it just comes out to -4, which is why this area is -4, this area is +4. And if we were to go straight from f of 2 minus f of -2, we'd just end up with 0. So our total area is actually going to be our two areas added together. So +4 here, -4 here. But we're not going to we're going to take the signs away because areas can't be negative in real life. Not in this case, at least. So +4, we're just going to take the magnitudes and +4. So it's 4 here, 4 here. Total area, 8. Okay. Okay. So now that we know the basic concept of areas, there's a few more flavors we have to understand. The first is they might ask you a curve, instead of bounded by the x-axis, which is this way, might add bounded by the y-axis, which is upwards. The way you do this is you shift your way of thinking from flip x and y. So you remember we're doing y equals f of x usually. Now we're looking for x in terms of y. So we have to work in terms of y, x in terms of y. So we have to express x in terms of y to get our curve. So I'm going to get x by itself. Y squared equals square both sides. Subtract away the 2y. X equals y squared minus 2y. And this is my curve. As you can see, it's a quadratic, but in the xy flip direction. Instead of smiley this way, it's sideways. What we're going to do is we're now going to integrate with respect to the y. Instead of before, when we were integrating with respect to x, we're now respect to y. What we do is it's actually x dy, but I'm going to write, since x is y squared minus 2y, dy. Integrate this. And since we're doing an area, you need your bounds. Usually you can find your bounds if you're not given an image by x at x equals 0. Substitute in 0 equals y squared minus 2y. Solve for y, and that gives you our bounds. So our bounds are, you can just look from the image 2 here, 0 and 2. I like to put that's 0 and 0, 0 and 2. It's good to put your bounds in while you're integrating. That way you don't forget about your bounds. You don't need to bother by writing a plus c anywhere. Okay, so now we integrate y cubed, increase power, divided by new power. And then increase power, this becomes minus 2y squared over 2. And since the 2 and 2 cancel, I'm just going to write minus y squared. I put my big square brackets to show my bounds, 0 to 2. So now I'm going to plug in. First I'm going to do y is 2. 2 cubed over 3 minus 2 squared. And subtract from, substitute in 0, which is just 0, 0. Because both of these become 0. And the value this gives me is minus 4 by 3. And it's minus because it's on the left-hand side of the axis. These are all negative x values. So when you write the area, you just write it as 4 by 3 units square. And the unit square means it's an area, because areas is a square. Okay, so that's our thing for x-axis. Here's another kind. They might ask you area between a curve and a line. It says curve. In these situations, the first thing you want to do is find the bound. And you can find the bounds by seeing where the lines cross. Here it's straightforward. I can just look at the graph. But if you don't have the graph, what you do is you simultaneously solve. So I would do 2x, this curve, is equal to this curve, 5 minus x squared, solve for x, right? And that'll give you 3 and 0, hopefully. Yeah, looks about right. 3 and 0. And we use these values of x as our bounds. And here's a key point with curves and lines is that in light blue here, no, light greens, the shaded area, the red area, is going to be area below blue curve, which I'll show in blue. Area below blue curve is like this, right? And we're going to stop at 3. This is below the blue curve. If we integrate blue curve with respect to x, between the blue curve and the x-axis, we get this shaded blue area. Now, if we integrate the line, or you could just do it like a triangle, triangle area base height, or I'd prefer to integrate it here. Area of the below curve, and let's do the area of below the green line. The area below the green line is this green shaded thing I've done here. And if we take the green line, the green shaded area from the blue shaded area, we're left with the red. You can see that, right? We take out from the blue, we take the green, and we're left with the red. So that's what we're going to do here in this question. Yeah, right. We're in this question. We're going to do integrate 5 minus x squared dx minus integrate 2x dx. And it's 0 to 3 for both. So area below blue curve, area below green line. And since they're both integrals, both have the same bounds, we can combine them into one integral. 0 to 3 minus x squared plus 2x plus 5 dx. And we
Should it
can
not be
solve
minus
this.
2x?
Oh, yeah, my bad. Minus 2x, because this constant outside actually multiplies in as well. And we integrate this to get minus x cubed by 3 minus, it's going to be 2x squared by 2. So I'm just going to write x squared plus 5x. Constant terms get x. 3. Now we plug in our values. For 0, this is going to be 0. And for 3, it's going to be minus 3 cubed over 3. You can start plugging this into your calculator. That'd be helpful.
I'm very confused because I'm getting a negative value. I think I made some
Oh,
kind of mistake.
oh, x is 3. Negative value.
Are you sure that the equations are correct? I think they should be correct, but like,
Hmm.
oh wait, oh it's 5x minus x squared, not 5 minus x squared.
Sorry.
It's you've written it as an integration of 5 minus x squared, which is not true because it's
Oh, it's
5x
5x.
minus. Yeah,
Whoops. Whoopsie days. Didn't read it
that's why like my
correctly
integral
here.
also got a weird value.
Right, if this is 5x here,
Okay,
it should
now
be
this
x
works.
squared by 2. So it's going to be 5 by 2, 3 squared. And what does that give?
I did it directly.
Uh-huh.
I got like 4.5. I might try what you also wrote here.
3 cubed by minus 3 squared plus 5 by 2. Whoops, forgot the multi sign. Yeah, 9 by 2, 4.5. So this is for the 3
It'll be
bound,
9 upon 2.
so 0 bound, and that gives 9 upon 2.
That
So
is
the
correct.
area of the red area here is 9.2, no, 4.5 units.
Also, by the way, I don't know if you also told, but there's also an alternative method of doing this. Essentially,
Yep.
what you can do is just take the area under the straight line y equals to 2x as a triangle. So
Yeah.
it's just going to be 6 times 3 divided by 2. And additionally, too, I think in the mark schemes, they do prefer if you state specifically how do you define the area. Like, for example, this one line, the shaded area equals to the area below the blue curve minus the area below the green line. Of course, you won't have blue and green, but like you could actually state that. You usually get a point or something. I'm not 100% sure, but I remember that in the mark schemes, they prefer
Mm.
it that way.
So you should be clear what your method is, not just numbers there, but maybe even a bit of writing to say that I did this method.
Especially when you're like subtracting two areas,
Hmm.
like to find the shaded area, do this minus this. It's like one liner that should give
Yeah.
you a point.
Yep. And sometimes this can get a bit more confusing. Suppose you have to find this area. I was considering not putting numbers in here to save time, but just it's I think important to know. Suppose you have to find this area. If you just go from here to here, integrate, this negative bit and this positive bit will cancel each other out a bit and you won't get the true area. So if you just did area under green line, area under blue curve, between the whole thing, it wouldn't quite work. So how would you find this area? Well, there's different approaches to this. I'll give one approach you can do. You can first find the points where they cross, obviously. 1 point is 0. That looks like, again, minus 3. So that's our bounds, some of them. But we could also use a bound here, minus 2. And the method I'd prefer here is I would find this area, right? And that would just be for the blue curve. I'll write in purple, or up here in purple, right? Purple box. This is integrate the blue curve, which is x squared plus 2x. It's the area this curve, blue curve, makes with the x-axis from minus 2 to 0. So minus 2 to 0. So that's one of the areas. Now I need to find the rest of the area. How can I do this? I'll change color here. Light blue. One way I could do this is I'd take the area of this triangle here, and from that triangle, I can subtract different color. This area here, wait, red. This area here, which is this area is area made by, again, that curve, and that's from minus 3 to minus 2. And take note, this will give you a negative area. This will give you a positive area. So you have to take account of those. And what I get for that blue section there, I could do that blue triangle minus that red bit will give me shaded bit. Do you get it? Okay. So I could get the area of triangle just by base height, or I could integrate. I think I'll use base height. So it's 3 across. Looks to be 3 tall as well. And that gives times half for triangles. So 9 by 2. So this has area 9 by 2. This I'll need to integrate. This I'll need to integrate. So I'll just speed through those because we have some more to cover as well. Let's integrate x squared, x cubed plus 2, no, not 2x, x squared minus 3 minus 2. I'm going to use my calculator for this. X squared plus 2x. Set bounds minus 3 minus 2. So for this, it gives me, once I plug in the values, gives me 4 by 3. For this, once I plug in the values, it should give me something negative. This gives me minus 4 by 3. So my final thing, we can write this in a one-liner. My triangle minus my red area plus positive value of my purple area, or whatever. So 9 by 2, I could color code it, but I feel a bit lazy. 9 by 2, which is our triangle. That's scrappy. I won't put that in. 9 by 2 minus our shaded red area, 4 by 3. And then plus our this bit here, which is again 4 by 3. Yep. So our final area again comes out to 9 by 2, oddly enough. Okay, so this sort of question is a bit difficult. It does come up sometimes though. Just formulate a strategy. How can I get this area? Chunk it up into sections and get the sections by themselves and assemble them to get the right area. Okay. This is like the little bit meaner version of area between curve and a line. Welcome to area between two curves. Same principle. And first of all, always you need to find your bounds. So solve simultaneously. I'm hoping you guys all know how to do simultaneous equations, and which is why I'm not bothering here. But if you want to, it's x minus x squared. Solve for x. That gives us 1/2 and 0. So let's speed through this here. Again, helps to visualize on the graph. So I'm going to do green. Area under green curve minus area under blue curve gives me red shaded area.
The thing is that
So I
both
could,
of these have the same limit, so we could just make it into one integral.
yes, sir. They both end here. So I could write one big integral going from 0 to half, and area under green curve. My green curve is, I'm going to write up here, x minus x squared, my green curve, minus x squared, my blue curve. And combining these, I'll get x minus 2x squared dx. And now I solve this. I get x squared by 2, 2x cubed by 3 minus limit 0 to half. And then again, you can do half squared by 2 minus 2 cubed by 3 minus 0 because 0. And when I do that, I'll get a small area in the decimals, hopefully.
I got 1 upon 2, 1 divided by 24.
1 by 24. Yep.
Is that
1
correct?
by 24. Yeah, that's correct. That is our area in red shaded there. Okay. That's between two curves. And again, like between two lines we can have here. I decided not to give the functions of the curve here just to speed it up a bit. But let's just formulate a plan for this one. Okay. Let's say green curve is f of x, blue curve is g of x, and they cross at minus 2 and 4. Write an expression for the area. Oh, by the way, it says here f dash of x, which means that's the derivative, and g dash. So when I want to write this represents the integral because I've gone from derivative to curve that's integrated. Sometimes you might see if f of x is the curve, you might see the integral version as capital F of x on some websites. But let's not worry about that. So anyway, these are the curves, and when I integrate them, I can just write f of x instead of f prime of x, or f dash. Which usually it's better to say f prime, I think. Okay, let's just work out a plan. Take a second to try this for yourselves. If not, I will, let's see, pick this apart. As always, I want to deal with the negative area first here. I'm going to deal with this box here. And for the purple box, I'm just going to write that's blue curve. So g of x, which is integrated already, since you see g dash of x dx means g of x, just for you wondering. And I want the bounds to go from 0 to 4. That's one. Now I'm going to do another one. I want this area here. Since that looks nice and clean by itself, it's just the area under the green curve here. So I'm going to write f of x, which is integral of f prime of x, going from, again, 0 to 4. That's another one. Now I'm going to get the third bit.
Wait, why don't you just take the entire integration of the green part from -4 to +4,
Negative
and just
4
like
to subtract this bit.
Oh, I just realized that wouldn't work. No, would that work?
It would work, but you'd have to get this bit separately. I think that's a good
Yeah,
plan.
and getting that bit would be very hard. Because
Oh, you
even
can
if we
just.
try to do the integral of the blue thing, it's only going to be till -2, you know?
Oh, yeah, true, true, true.
So it's not going to cover some bit. So yeah, your method would work here, yeah. You should do it like this.
Okay. And now I want this bit here. I'm dealing
Or
with.
wait, actually, wait, you could
I
have
mean, you
just
could
done.
just run from 4 to this, right?
Yeah, yeah,
For
yeah,
the
from
green
-2
green
to
curve.
4. Yeah,
That's good.
that
That's a good way
those
to do it.
limits.
Let's do it that way.
So that'd be like one less a shape to consider.
Mm-hmm. Yeah. Saves time. So we go like this. Area under the green curve is in blue. Yeah. From -2 to 4. And from that, we subtract our little red portion here, which is minus g of x integrated. Remember, that's integrated, guys. -2 to 0. And that'll give us the shaded red bit. Do you get it? From that big blue bit, we subtract a little red bit. So since this would give us a negative area, I'd write this as positive here. Wait, no, negative to give it a positive value. Okay, so my expression in finally would be f of x. Well, they won't ask you in write an expression, but this is just to like get the point across. Minus g of x to show you which shapes to add up, basically. 2 minus g of x from 0 to 4. And that gives us the final shaded red area. So be aware and do a lot of practice of adding up shapes that are like this, where you have to get different sections. Okay, that's the area stuff covered. Now let's just deal with two special cases that we have to work with here. First is improper integrals, and the second is something mind-blowing that we'll save for a few minutes. Okay, look at these integrals. Which one has a finite value, which one does not? Should be obvious by looking at it, right? That just goes from 0 to 10. Obviously, 10 squared is just 100. That's finite. But even if you integrate it, if you get 10 cubed by 3 and you get 1,000 by 3, that's the value of this, right? That's finite. But to infinity, what? What even is this? That's not finite, is it? So this is infinite. This is finite. Cool. Very basic idea. You don't need to know much about infinity to judge that. So now let's look at another case. Which one of these has a finite value and which one does not? You might at first glance think, oh, that has infinity in it. It must be an infinite value. However, what's happening here is, first let's just integrate this. 1 by 2, 1 by x squared, when you integrate, becomes, that's like x to the power minus 2, right? So it becomes x to the power minus 1 by minus 1. So it becomes 1 minus 1 by x, I believe. Yeah. With the bounds, a and b, whatever. So if we were to go from 1 to infinity, 1 divided by infinity is actually 0. Think about it. If you want to divide, you have a piece of chocolate you want to give out, and you just keep on giving it to infinitely many people. Now, infinitely is a lot. So at the end, if you divide it all into equal pieces, everybody's going to get nothing because you just gave it out so much that it's gone. So you've divided it into so many different bits, so infinitely many bits, and it's 0. Everybody gets 0, right? So this 1 by infinity is actually 0. So that means minus 1 by 1 minus 1 by infinity is actually, this becomes 0, this becomes minus 1, minus 1 by 0 is actually just minus 1. Whereas this, if you were to do 1 by x minus 0 to 10, you'd come up with a problem. Why? Well, 1 by 10 is fine, right? No problem there. But 1 by 0, you cannot divide by 0. No, because it gives you an infinitely large value. So you can think of these guys as opposites. This has a finite value now. This has infinite. 1 by 0 is infinite, by the way. Undefined. People don't write infinite, usually write undefined, because your calculator can't show that. Next slide, we'll see what it looks like on a graph, but for now, just understand if the fraction is on the top and it goes to infinity, it's infinite. If the fraction is on the bottom, it goes to infinity, it's finite. And whereas the 0 on the bottom makes a problem, 0 on the top, not problem. Infinity on top, problem. Infinity on the bottom, not problem. Okay, with that knowledge, let's formally define informal integrals, improper integrals. One of the values at a bound is undefined, or one or more of the bounds is infinity. And not all improper integrals will have a finite value, a defined value. Some of them might be infinitely large. So if they are infinitely large, you can't solve them. But if they aren't, then you can. So not all of them have a finite value. To check if they have a finite value, we first integrate. Replace the troublesome bound with variable, and we find out what happens as p approaches. So I'll use this method to solve these, because this is the way Cambridge wants you to do it. Let's go -2 to 0. And first time I'm going to integrate this. I can see that 0 at the bottom of the fraction is going to make a little issue there. So I'm going to replace 0 with p. I'm going to 2x to the power -5 dx. That gives me -5 minus 4, 2 by -4, x power -4. And 2 by -4 is like 1 by 2, right? -1 by 2 x. And this is from limit 2 to p. So we're going to write this limit out, this box. -2 to the power -4. Wait, upper bound is 0. So this, and then -12 p to the power -4. And this you can calculate, like, no worries. But this -12 1 by p4, as p approaches 0, you have to write it like this, with the little arrow meaning approaching. As p approaches 0, you can just write 1 by p to the power 4 approaches infinity, because as the bottom of the fraction gets closer and closer to 0, the fraction itself gets larger and larger, and it approaches infinity. So that means if this bit is infinity, then the integral itself cannot have a defined value because that's infinity. So this is not finite. That's how we formally write it. Let's do the other one as well. Same thing. Let's say we've integrated already. Minus half x power minus 4. And our bounds are minus infinity. I keep writing 8. It looks like an 8, doesn't it? Minus 2. So of course we write our bound for minus 2. And then we write our bound for infinity. And we replace infinity with p for now. Minus half. It's like 1 by p power 4. Here, as p approaches minus infinity, if we divide 1 by infinity, as the bottom of the fraction gets larger and larger, fraction itself gets smaller and smaller. So 1 by p power 4 actually tends towards 0. As p tends towards infinity, minus infinity, p tends towards 0. So eventually, this will just be 0. And our final integral, with this becoming 0, will just be, that's where our value comes from. So this is finite and has value. We ignore the part which was 0, and we just look at this. So let's calculate that. Minus 2 to the power minus 4.
Negative 1 upon 32.
Yeah. So that is minus 1 by 32. Because this is minus 1 by 32. 32. And we
Wait, is
subtract
it
0 from it.
positive or is it negative? I'm confused now.
I think it should be negative because minus 2 to the power 4 becomes
No,
positive,
it
right?
should be. Oh, it should be negative, but my calculator. For my okay, I think I know why.
Because it was your power. There was no brackets, right? The power.
Yeah, it was
Yeah.
like just doing 2 to the power negative 4, not negative
Mm.
2 to the power negative 4.
Okay, here are a
Brackets are
few
important, kids.
graphs. Yeah. They're hidden behind the writing a bit. Guess which is which. This one is this one. And as you can see, as p tends towards 0, our 1 by p power 4 tends towards infinity. You can see this graph going straight up, and it'll never actually touch the axis. But you can assume that as it tends towards, it will tend towards. It just keep going up. By contrast, this one is finite because it's going towards the axis. Oh, the shaded area is just getting bigger and bigger. It's infinity, right? This area, it's tending towards the axis, and you can see it's getting smaller and smaller, tends towards 0. So basically, it's just, it's a finite area. It's getting smaller, and it'll eventually get stopped. Okay, that was improper integrals. One last thing. I know there's a lot of theory, but there will be questions. Volumes of revolution. Sounds fascinating, doesn't it? Water bottle. I have a nice way to explain this here. Look at this graph down the x-axis. This is the y. This is the x. Imagine, right, 3D space. This is x. This is y. Let's ignore this axis for a second. Just that's for reference. My eyeball is looking at it this way, right? I'm looking down the x-axis, and I rotate it a full rectangle about. So I rotate this How about the I rotate this about the x-axis. I'd make a cylinder. You probably guessed as much. Write down an expression for that volume of the cylinder. Simple enough, isn't it? Um, it has a radius 1. It has length 4. So volume will be, oh, actually it doesn't have length 4. Length can be whatever you want. Length is x. So it's radius 1, length x. So our cylinder is, we know, pi r square times h, because we've rotated this to make a cylinder, sort
I
of.
guess that would
Get it?
just be x in this case, right? H.
Yeah. So our volume is pi, radius is 1. So just 1 squared, just 1, pi x here. Now let's take a different thing. I'm not going to stop at a line, at a straight line. I want a line with a gradient on it now. Here's my line. If I rotate it about the x-axis same way, around like that, or a bit bigger around like that, you get what I mean, right? I get a cone looking at it. Right now, an expression for the volume of that cone now. If you've done some maths, you should know that a cone is 1 by 3 pi r square h. That's right. Yeah. Yep.
It's gonna be funny, but I don't really remember the formula of the cone. I think it was in the MF19
I hope this
thing.
is it.
Let me just
Yeah.
check really
Yeah.
quick.
This is it. Pretty sure.
1/3 times base area times height. So in this case, base area is just pi r square. So yeah. Mhm.
Okay. And this again, no, this we don't know where it ends. It just goes up x. Oh, and the slope is line is x equals y, right? Slope is 1. So what our volume will be in this cone, volume will be 1 by 3 pi radius of the cone. The radius of the cone is actually y, because the radius is going to be y, and that's changing, but y is just x. So you can write radius is x squared. And interestingly, look here. What's the height, or like how far it goes in this direction? That's also x. So interestingly, our volume is 1 by 3 pi x cubed. Curious, huh? However, I've been struck by a madness. I won't stop at lines. I want to rotate a curve about the x-axis. How can I do that? Well, believe it or not, we're going to start cutting things into slices. Look at this thing. So we've taken the curve, rotated it around 360 degrees around, to make a solid, right? And the solid, I've cut it up into slices. If the slices are extremely thin, say delta x or dx thin, then each slice is basically a cylinder, because that curve here, that curve on this edge, doesn't really matter at that small a scale, just a cylinder with a straight line. Hoo-hoo. And the radius of that cylinder is my y value, y. And its dx is the thickness of that cylinder, the height of it, right? And since we know the volume of cylinder is pi r square h, you can replace r and h to get pi y squared dx. And now you've probably guessed where this is going. If we want to now total up all those slices using our little sum of integral, And of course, between two bounds, bound A and B, our integral will be written as this: pi, since it's constant I can take outside, sum of all y squared delta x times delta x. So it's just basically adding up all the slices, and the slices are pi r square, with r being y. So y gets squared. Now note that y represents the curve, and if y is x plus 1, then remember y squared is actually x plus 1 whole squared, not like x squared plus 1 squared, no, whole squared. Okay, whole squared. Let's do a practice question for this. And this is a tricky practice question by... Oh, actually, before we go that, let's go back. Little thing. Let's prove that this is a cone, right? If I want to go from... If I have y equals x, and I'm getting the cone value, then watch this. Remember I said pi y squared dx, right? Then my y is equal to x, so pi x squared dx, integrate this, pi, oh, this is 0 to x, by the way, pi x power 2 plus 1, x power 3 by 3, the dx goes away, and from 0 to x. 0 doesn't matter, so just
It's just gonna be
our...
pi times x cube upon 3 because we're just gonna substitute x into x.
Yeah, x gets into x. So that's where this comes from, volume of this. Pi x by 3. Awesome. Fun bit of trivia. Unnecessary, but pretty cool, I think. Okay, back to volumes proper. Here's a tough question, just because here the temptation is to put this thing, y equals 3 minus the curve, and put them together and then square them. But this is like saying y squared. This is like saying if y equals 3 and y1 equals 2, y equals x, then 3 minus... This is like saying 3 minus x whole square is actually the same as x squared and 3 squared. The point is, a squared minus b squared does not equal a plus b whole square, right? They're separate things. You can't group them together and square them. You have to square them separately, which is what I'm saying. I've
No, but
fallen
like
into
if
this trap myself once. Yeah, go ahead.
I think like if we're trying to rotate it along the y-axis, right? Is it not just gonna switch
Oh,
into like x square? Like I mean like pi times integral of x square with respect to dy.
oh yeah. For the y-axis, we can do separately. I'm talking about the x-axis one here.
Oh, okay. I was just confused with the shaded
Sorry.
region.
Yeah. Um, sorry.
Oh, I know
So if
what
we're
you
going
were trying to
around
say.
this way,
Okay. So it's like a cylinder plus the value of the thing. Okay.
uh-huh. So what we actually have to do around the x-axis is we have to take this whole cylinder, you see, this red cylinder, which I've drawn very shakily, and from that we have to subtract our... change color here. We have to subtract our blue curve shape. A bit unclear, but let's do this here. So what we have to do is find the value of the volume of the red cylinder, which is 4. I'm just going to use volume of cylinder is pi r square h. Volume of red is pi. Radius is 3. 3 squared is 9 times 4. So that's just 36 pi. Volume of blue. Here we have to integrate. So for blue, y is equal to square root 2x plus 1, right? So y squared is equal to just 2x plus 1. So if we integrate y squared with respect to dx between 0 and 4 with times pi, same as saying 0, 4, pi, y squared is 2x plus 1 dx. That will bring us to 2x x squared plus x integrated. Pi you can keep outside because you're multiplying. 0 to 4. And 4 squared plus 4 is 20. So this gives me 20 pi for the red. So for about the x-axis, it's going to be volume of red minus volume of blue. So 36 pi. Red cylinder minus blue cylinder, 20 pi. Volume is 36 minus 20, 16 pi. Which is, I'll draw it in a different color here. Imagine this thing. See this purple bit here? This purple bit here? Imagine this going around with like a hollow thing in the center. No, not like that. Like a hollow thing in the center. It might be a bit tough wrapping your head about 3D. Just like Desmos does have a 3D thing. I'm not sure if you can graph this stuff at this level though. So just maybe watch a video of 3D representation of this. Pretty helpful to visualize. Okay. I think let's just go through going around the y-axis real quick. The different thing. So imagine I want to go like this. This. I've rotated about the y-axis instead now. So simple enough here. If y equals root 2x plus 1, remember you just switch your working from x to y. So y squared equals 2x plus 1. I'm getting y squared minus 1 by 2 equal to x. So I've got an x in terms of y. Clear enough right now. And now I'm going to do x squared. No. Yes. X squared dy. Remember, I've just flipped x and y. My bounds go from minus 1 to 3. 1 to 3 along the y-axis. Pi. And if this is my x squared is this squared. So x squared is equal to by 4. I just squared the 2 at the bottom. Y power 4 minus 2y squared plus 1. So my integral would be pi. I can put the by 4 outside actually, since it's a constant. Y power 4 minus 2y squared plus 1 dx dy because we're working y-axis. You guys can solve that, or since I've come this far, let's just finish it. Y power 5 by 5 minus 2 by 3. That's a horrible 3. Y power 3 plus y from bounds. Always write your bounds. 1 to 3 pi by 4. Okay, I'll just use my calculator here because I don't want to plug in every value.
I got 496 upon 15. Wait, oh, times
I'll
that by. Wait, I need to divide that by 4. So it'll be 124 divided by 15 pi.
124
Divided by 15
divided
pi.
15 pi. That's our final answer. Swaggers. Yeah, reasonable. So around that axis, that's how you do it. Remember, just switch x and y when you're looking at another axis. Okay. Whew, that was a lot of information. Now let's start putting that information to use in our exam questions. You want to take the first one?
Sure, yeah, why not? So it says that the equation of a curve is such that dy upon dx equals to 3x to the power half minus 3x to the power negative half. The curve passes through the points 3, 5. That, by the way, I think would result to the value of c later. And so essentially what it's asking is find the equation of the curve. Now, according to the weird explanation that I had, right, we essentially put dx upon to the right side. So, and then on the left-hand side, it would be 1 times dy. So like integral of 1 with respect to y, which would be y. And on the right-hand side, it would be integral of whatever we have here with respect to dx. And then we just put the integral signs on both sides. And so essentially on the left-hand side, it would turn into, as it would be like, let's say y to the power 0. That would be 1. So y to the left-hand side. And then on the right-hand side, it will be equal to, let's solve this. So 1 upon 2 plus 1 is equals to 3 upon 2. So it'll be 3x to the power 3 upon 2 divided by 3 upon 2.
Wait, oh, 3 by 2 divided by
Yeah. And then it'll be minus 3. There should also be an x there, 3x.
Oops, my bad.
So it'll be 3x to the power half divided by half.
X to the power half divided by half.
And we could just simplify plus c.
Plus C.
I
Plus
almost
C.
forgot. So now what we do is that 3 divided by 3 upon 2 is basically 3 times 2 upon 3, which is 2. 2x to the power 3 upon 2 minus 6x to the power half plus c. And now what we do is that we have been given a point, which is 3, 5. So we just basically put this into the equation to find the value of c. So it'll be 5 equals to 2 times 3 to the power 3 upon 2. Let's just like substitute it all. Minus 6 times x 3 to the power half plus c. So it's going to be 5 equals to 3. Wait, let's see what this is. Oh, wait, I'm getting a weird value. I guess the answer would be in thirds either way. So, especially for the value of c. So it's just going to be 3 cube. So it'll be 5 equals to 6 roots 3. 5 equals to 6 root 3.
6 root 3.
And then it'll be root 3 times 6. Oh, minus 6 root 3.
Whoa, awesome.
Let me actually just confirm this.
Looks reasonable.
Minus 6 root 3. Yeah, that's, and then plus c. So essentially here c would be equal to 5. Simple as that. And now what we do is this. We look at the equation that we have with the value with the c and replace that with 5. So it'd be Yeah, this one, yeah. So it'll be y equals to 2x to the power 3.2 minus 6x to the power half plus 5.
Yep. And indeed, that is what it is. Okay. 1 mark for integrating and 1 mark for simplifying. Oh, actually, 1 mark just for integrating both parts correctly. 1 mark for each part. Getting C. Okay, awesome. Ooh, this question. We did this question last time, but it was a differentiation one. Here's the integration part of that question. You'll find that integration and differentiation questions are usually paired together on the past papers. So right, let's find the area of the region between the two curves. Now between the two curves doesn't mean out here or out here, no. Oh, it means this region bound by the two of them, between them. How can we find this area? Well, what I can already see is they've given me the point B, so I don't need to simultaneously solve or anything. And this is obviously just 0. So this is 4 in the x-axis. What it looks like is I can do from the above curve, I can subtract the lower curve. That's a horrible color. Where'd my pen gone? Subtract the bottom one, which looks like that. So from that red outline, I can subtract the purple outline. Yeah. Purple outline. Just gonna make it smaller. Okay, so red minus purple gives green. Cool. So what I'm gonna do, since they both have the same bounds, up to 4, up to 0, I can combine the integrals. So I'm gonna do the integral of red is this one, red, 2x half plus 1 dx from 0 to 4. That's red minus purple, 0 to 4 again. Purple is this one down here, half x squared minus x plus 1 dx. I'm going to combine these. Oh yeah, looks good. And a single integral, 0 to 4. I'm going to go with half x squared. Oh no, minus half x squared. Let's go in order so it makes sense. 2x half plus 1 minus 1. Oh, by the way, this minus sign carries over to all of it, by the way. Minus 1, 0. So this gets cancelled. Minus half x squared minus minus plus x dx. Integrate this real quick. We're going to get 2x 3 by 2 over 3 by 2 minus 1 by 2 x cubed by 3. I'm going to simplify this in a second. X squared by 2, right? Bound from 0 to 4. I would simplify this just so I can type it in quicker. Or you don't even have to simplify it. You could put in your calculator just like that. I'm going to put 2 times 3 was there. I'm going to put 1 by 6. 2 over 3 over 2 is 4 by 3. 4 by 3. Yeah. So now I've simplified it. I'm going to plug in my values. Basically, 4 to the power of 3 by 2. Vyom, can you be typing this, please, while I write this?
I'm trying to do the integral like directly, and my
Oh, sure.
screen has gone blank. It's taking
Oh.
its time to load. That usually happens a lot with some difficult integrals. The
Mm-hmm.
calculator just goes blank for some time, and then like maybe like a few seconds later, it will just like pop up like, "Oh, I'm alive."
And it looks like the second one is indeed 0. Is it still blank or did it pop up yet?
It was still blank. Let me try this again. Actually,
Sometimes if you like mistype something in and the calculator literally cannot integrate that, then it'll pause. Syntax error. I guess my favorite answer. What did I do?
mine
Oh,
is
that looks
like
better.
still loading for some reason.
Okay, I
Like,
got 8.
okay,
Seems
wait, did
reasonable.
you do like the integral of it? Look,
No,
just you know
I
what?
just
Okay,
typed this in.
let's not rely on technology and instead use our brains. Okay, so let me
Okay,
just go back to
8.
scratch. So it'll be 1 upon 2, 3 upon 2, 2 divided by 3 upon 2. So that's 4 upon 3, that's correct. That'll be 3, 1 upon 6. And then we just put in the values into that. So 4 to the power 3 upon 2 times 4 divided by 3 minus 1 upon 6 times 4 to the power 3 plus 16 upon 2. I got 8. Yeah,
Awesome.
8.
Indeed, it is 8. 1 mark for showing that you subtract the 2. 1 mark for integrating. 1 mark for plugging in the values, the bounds. 1 mark for the answer. Awesome. Ooh, you want to do this one, Vyomesh?
Yeah, sure. So it says, okay, it's an indefinite integral. So in this case, just integrate it normally. I would just go with 3x. It's essentially 3x minus 2 to the power negative 3 upon 2, right? Uh, I I don't exactly remember the exact formula, but I think it was like you just increase the power of it by 1. So it will essentially turn into like, let's make the bracket first.
You mean
Oh, yeah,
like
let's
that?
just go with the integral sign too. So it's gonna be a bracket,
Oh, yeah.
like the bracket, like the square bracket.
Oh, the square bracket. No, my bad.
Yeah, so that would be 3x minus 2 to the power negative half. Then divided by 3 times negative half, which is negative 3 upon 2. Well, yeah, it's fine as it is. And the limits would be 1 and infinity.
Mm-hmm.
And that will be, we could just put in the values. So for if we put, okay, if we, let's rearrange that a bit, I think. We could put the negative half below
Mm-hmm.
the power. So it would just turn into actually if it is negative 3.2, right? So it'd be from the we could just take that outside, I would think. Negative 3.2.
Oh, right. Minus 3 by 2.
And then there will be a square bracket.
What just happened? It just unhighlighted half my screen. Okay.
And then the other thing
Anyway.
would be 1 upon 3x minus 2 to the power half. And with the limits of 1 and infinity. And that simply shows us this, that if we put infinity there, right, then it's
Mhm.
gonna be infinity on the denominator. And if it is an infinity on a denominator, that essentially equals to 0. So this would be
Yeah.
definite integral. Oh wait, no, I'm confusing stuff wordings. But essentially, what it means is that it's gonna be, there's gonna be a discrete value. Because if we put infinity in the value of x, this would go. Yeah, if x leans towards infinity, it's gonna be equal to zero. This whole entire value is gonna be equal to 0. Yep. And then after that, we could just put in the value of 1 here now instead. So 3 minus 2 to the power of half, which is 1, times negative 3. So it's basically 0 minus negative 3 upon 2. Because if we put 1
Wait,
there, then that would just be equal to 1.
1/2 minus 0. Because
No, it shouldn't be the other way
infinity is the
around.
top one, yeah. I
Yeah, so
can't
it would be
seem to
0
erase it right
minus
now.
that.
0 minus
So the value of that would be just plain 3 upon 2.
2.
There we
That's
go.
our
I think
answer.
that should be it.
Yeah. Wait. What?
Oh,
Did we
wait,
make
I made a
mistake in
mistake.
simplifying?
I made a
Oh
mistake.
yeah, the 2 is on the bottom, so it would go up top. So, whoopsie,
Oh, yeah, it'll be 2 upon 3.
2
Yeah,
by
it'll
3.
be flipped. If it is
Um,
negative 3 upon 2 below, then it's going to be negative 2 upon 3 above. That makes sense.
yeah. Hope you guys caught that. I don't know why my PowerPoint's bugged again. I think I'll close and open it. One sec. Keep annotations. Gotta make sure to reshare it this time. Share screen. Okay. I shared the presentation screen.
Okay, there we go.
Right. So it was 2 over 3 because simplifying thingy. Because it was 3 over minus 1/2. No, wait.
No, wait,
3 was on the
essentially
bottom.
yeah, it was negative 3 upon 2 at the bottom, and so when it flips, it turns into negative 2 upon 3. Yeah,
Yeah.
like that.
Okay. M1 for applying limits. So either you can show them that 0 is just becomes 0. I'd like to put, like, instead of infinity, I'd put a variable, and I'd say as p tends to infinity, the whole fraction 1 by p half or whatever tends to 0. Just as long as they see that you've done the concept and you've gotten 0 there. Okay. Volume here. Volume of revolution. Interesting question here. Okay. Diagram shows curve this. The shaded region is bounded by the curve, x-axis, and lines 1 and 2. So this shaded region is bounded by these lines, x is 1 and 2, the curve, and the x-axis. The curve and the x-axis. Okay, so we know that. They're just telling us again. It's rotated 360 around the x-axis. So like that. Yeah, to make our slices. Like that. Find the volume of revolution. Okay, hope you remember the formula, which goes something like pi r squared, where r is y, times dx. Thickness. Okay, simple enough here. Y is this, where y is 3x minus 2, 3 by 2, minus, because that's the bottom of the fraction. So y squared, since they're in brackets, we can just square the brackets bit without any problem. If I square this, remember guys, if I square this, then the 2 and the 2 multiply, which is why we just end up with minus 3. So this is y squared. Now I'm going to integrate. And I'm going to integrate from bound 1 to 2. And I keep my pi outside. And I put in my y squared, which is going to be 3x minus 2 minus power minus 3 dx. And this will give me pi outside the thing. 3 by 2x squared minus 2x. No, what am I doing? There's a power. Wait. So wait, this is a bracket. So 3x minus 2 to the power minus 3. We're going to increase minus 3 to minus 2. Divide by minus 2. And multiply by the factor of the x, 3. 1 to 2. Clean this up to make... Okay, just clean this up. Minus 2 times 3 is minus 6. So now let's plug in the values. Keep the pi outside. Pi times... That's a big bracket. For the 2, 3 times 2 minus 2 over minus 6. Oh, power minus 2. Pi goes around both, by the way. And then for the 1, 3 minus 2 minus 2 by minus 6. Let's get the value for that without the pi first. 3 times 2 minus 2 to the power minus 2 over minus 6. So I like to write the sections out separately. Minus 1 by 96 minus that's 1 by 6 minus 6 minus 1 by minus 6. 1 by minus 6. Yeah. Times pi. Which will give me by 96 plus 1 by 6. 5 by 32 pi. Which seems like an odd answer, but...
It is correct, I think. Yeah.
Yeah.
You know what's kind of funny
These
though?
answers do look odd. Yeah?
I did the entire calculation on whatever you did in one calculation. You can't see, but like in one line, I got 5 upon 32. Flex,
Also,
but no.
calculator, or did you algebra do that?
Oh no, calculator.
Oh,
Like this just shows like how quick it is to actually check your answers using the calculator. Like it took me like way less time.
always good to check. Minus 1 by 6. Apply limits 1 and 2. Oh yeah, they're saying apply the bounds. Okay. Would you like to do this one? Oh my goodness, 5 marks.
Sure. So it says that the equation of a curve is such that d squared y upon dx squared equals to 6x squared minus 4 upon x cubed. The curve has a stationary point at this. If it says that it has a stationary point at this point, okay. So first of all, what I would do is that I would integrate this, right? On both sides to give so it'll turn into integration of 6x squared. So oh wait, sorry. D of y upon dx is equal to different integration of 6x squared minus 4 upon x minus 4x to the power negative 3 dx, and so this would turn into dy upon dx equals to...
Oh yeah, one new line.
Oh yeah, that also works.
Upon
Equals to...
dx equals to
equals to 6x cubed upon 3 minus, plus 4x
Oh,
to the power negative 2 upon 2. Because essentially, if we would have put negative 2 there, it would have been minus minus. Or we could keep it like that, yeah.
yeah.
Wait, should we? Yeah, okay. And then it would just be plus c, which is
Nice.
equals to, we could simplify this a bit more. It would be 2x cubed plus 2x to the power negative 2 plus c. And now it says that it has a stationary point, right? So it means two things, okay? First of all, the graph of the actual curve has a point at this coordinate, first of all. And second of all, it states that the gradient at this point is going to be 0. Okay? So now we have the equation of the gradient. And so we can equate this to be equal to 0 and put in the values of x, which is negative 1. So it's just going to be 2, like we just substitute the negative 1 value into this.
Okay.
So it'll be 2 times negative 1 cube plus 2 times negative 1 to the power negative 2 plus c equals to 0. And now
Minus 2
yes, so that's
plus
just going to
2.
be minus 2 plus 2. So c is equals to 0 essentially in this case.
Yep.
And now, so now we have an equation for dy upon dx, which is 2x cubed plus 2x squared. 2x to the power negative 2. Without the c value, because c is equal to 0. Now what we do is that we integrate this again. So we're going to get y equals to...
Well, yeah. Y
yeah,
equals 2.
2x to the power 4. Or, yeah, we could keep it like that. 2x cubed plus 2x to the power negative 2 dx. Remember, dx is essential. It's very important. And that will turn into is equal to 2x to the power 4 upon 4 plus 2x to the power negative 1 upon negative 1 plus c. Now, this is a different c. Sometimes people might just go with a d instead of c.
Mm.
I think a lot of Marxians do that, but c is also okay in this
My
case.
math teacher writes it's like C1 and then C2.
Oh, okay. That's also a creative way. So now what we do is that we put in the values of negative 1 and 9 upon 2 into this. So it will turn into... Let's actually simplify this a bit to just make it simple, right?
Mhm.
This is going to be y equals to 1 upon 2 x to the power 4 minus 2 upon x, or x minus 1, whatever works. Yeah, plus c2 equals to, yeah, that's given. And now we put in the value. So it'll be 9 upon 2 is equal to, we would substitute in the value of negative 1 minus 2 upon negative 1 plus c2. And so now we just need to make it in terms of c2. So it'll be 9 upon 2. Negative 1 to the power 4 is just 1. So minus 1 upon 2. And then there is minus 2. So c2 would be equal to 2.
Plus 2.
Yeah. Yeah, that should be it. And so we just put this back into the equation now. So y equals to 1 upon 2 x to the power 4 minus 2 upon x plus 2.
Wait. Oh, because this is plus, so this should be minus.
Yeah.
Okay, y equals
1 upon
half
2 minus
x to
0.5 minus
4
2. So that should give us 2
minus 2 by x plus 2.
plus 2. That should be it.
Yes. And indeed, it is it. 1 upon 2 is 2 by x plus 2. Right, 1 mark for integrating the second derivative, getting the c, integrating again, getting the other c, substituting, and then getting the full thing. Oh, also, some of you might have picked up, we wrote c1 and c2 separately because they are different constants, and we just don't want to mix them up there. Or they could be the same, but they're from different equations.
I think like
So they
the
are
marksman used
different
K,
values.
right?
Oh yeah. Here they use c, here they
It
use
doesn't
k.
matter really. You just need to
Any
differentiate
variable,
between these two.
Okay. Here is a line and a curve. Shows diagram this. Find the exact region bounded by. And you'll notice they haven't given us the points, which means we need to find them. Duh. Okay, number 1, let's find the bounds. Simultaneous equation, go. 2x plus 2 equals 5x power half. I'll look write it as root x because I like that. How that. Oh no. Wait, I'll close and open the PowerPoint again. It bugged again. Keep going fast. I don't know, man. Microsoft, you gotta fix your product. PowerPoint kinda sucks. Okay. PowerPoint, ready. Right. So in this question, we are not given the bounds. You'll notice that first thing. To find the area, we need the bounds. So we need to find the bounds first. I'm going to do this by doing simultaneous equation, make y equal y. Da, 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 da. How do I solve for x? Well, I could square both sides to get 25x equals, I'm going to square both sides here and get 4x squared plus 2 times 2 times 2, 8x plus 4. I could bring everything over to one side. 24, 8 minus 24, 17. And I can solve this however I wish. Quadratics. Yeah, I'm gonna pretend that I factorize that. 4x minus 1 equals 0. So x equals plus 4, x equals plus 1 by 4. So now I know this is 1 by 4, because this is less, this is 4, because it's more 1. Now that I know my bounds, I can now carry on with the rest of the question. First thing, I know, oh my goodness, I know what the curve is, I know what the line is. So the area will be the curve minus the line, it seems. In this section, at least. I'll do fancy colors. Here's the area under the line in green. And in red, here's the area under the curve. Hope that's clear. Yeah, I've gone a bit above the boundary to make it clear. So red minus green equals shaded, right? So let's do that real quick. Area under red is from 1 by 4 to 4. 2x. And red curve is 5x square root. And minus 1 by 4, 4, 2x plus 2 dx. I could combine this integral into 1, writing 1 by 4, 4, 5x half minus 2x minus 2 dx. I could then put it together. 5x 3 by 2, divide 3 by 2 minus 2 by 2 x squared minus 2x, limit 1 by 4 to 4. And again, I could simplify these. I could put the 2 above to get 10 by 3. Yeah. And once I put in the values, Vyom, can you be getting the value for this, please, while I write it?
I tried to do the integral thing.
Uh-huh.
It gave me like a decimal value.
Oops.
So I'm just gonna put in the values that you have.
Okay. X squared, 4 squared, minus 2 times 4. That's my first one. And my lower
That should
bound,
be 8 upon 3.
8 upon 3. Yeah. What? Oh my goodness. PowerPoint, not it today. He just annihilated another section of my thing. Anyway, 10 by 1 by 4, 3 by 2 power 3 minus 1 by 4 squared minus 2 by 4, let's say, and whole bracket. Let's do that. 10 by 3.
So it just turned into like 8 upon 3 minus 7 upon 28.
Wait, let me just write that down. 8 upon 3 minus, what is it?
7 upon 48.
Wow.
So it would be like 45 upon 16, I think. Well, oh, I could actually just, okay, it should be like 2.81 something. So I can like cross check. Oh, yeah, it should
Oh,
be correct. Yeah,
45 over 16.
it should be correct. Unless we messed up with the limits.
This is our area. And yes, indeed, our 2.841. SB exact answer. Thankfully, the decimal does cut at that. Line meets curve on this. Okay, one more. Trying the simultaneous and getting the values of x, integrating, or writing the integral, integrating, finding the answer. Oh, here's an alternative method for this, actually. What is it?
I guess they just used a triangle. I mean, a trapezium to find the area.
Oh, yeah. So instead of integrating that line, they just trapezium. You saw that, right? Okay. What is going on? Anyway,
Oh,
we're at the end.
I don't know. Anyways,
So
yeah. Thank you all for tuning in. We just hope that you had a great understanding of the concept. It's a final chapter too, so like congratulations. You could get hold of the ZNotes notes on the website, and our social media handles are on display. So contact us, and feel free to drop any questions. And I guess this is the end for Pure One Mathematics. See you in later future uploads. Then bye bye.
bye-bye. Happy revision.